The way data is sent on the internet is commonly described using a four-layer model. The layer at the bottom is called the link layer. This is the actual physical network that connects computers together. For example, in your home network, you're most likely using Ethernet to connect your computers. Other networks, especially larger networks, use alternatives to Ethernet, but the point is that it doesn't really matter. As long as you have a link layer that can transmit data, that's all that's required as far as the internet model is concerned. Above the link layer, we have the internet layer, which consists primarily of IP, the Internet Protocol. This is the layer responsible for addressing. When you send data, you need to specify what computer it's supposed to go to, and so we specify an address in the internet layer. The next layer up, the transport layer, exists for two purposes. First, when we send data to another computer, we need to specify which program on that computer is meant to receive the data. So for that purpose, when we send data, we specify in the transport layer what's called a port number. The other role of the transport layer is that very often when we send data, we want an acknowledgement that the data was actually received. And if we don't get back that acknowledgement, we want the data to be automatically resent. For this purpose, we use the transport layer protocol called TCP. The other transport layer protocol, UDP, is used when we don't care about reliability. UDP simply specifies a port number. Now, this may sound odd because when would you ever not want reliability? Well, actually it turns out there are plenty of cases where we wish to send data, but we don't care all that much about reliability. And so those are the cases in which we would use UDP. Finally, the top layer is called the application layer because it differs for different applications. For example, web browsers serve a very different purpose from, say, email clients. And so, whereas web browsers primarily use an application layer protocol called HTTP, email clients use different application layer protocols, including one called SMTP. So, whereas the internet layer and the transport layer, IP, TCP, and UDP, are all meant to be general purpose, application layer protocols are more specific. HTTP and SMTP are actually just two examples. There are hundreds of others. Now let's look at how these layers actually fit together, and let's assume data is being sent over Ethernet. Data over Ethernet is sent in discrete chunks called frames. Each Ethernet frame starts with a header, ends with a footer, and in between is the actual data being sent. The header and footer contain information about the frame itself. Most importantly, they specify a destination Ethernet address. Addresses in Ethernet are called MAC addresses, MAC. And the way Ethernet works is that any frame put out on the network is actually read by every single other computer on that network. Each computer on the network checks the MAC address of each frame to see if it matches that computer's own MAC address, and if so, a computer knows that that frame is intended for itself. It's pretty much like if we were to send letters to each other by just dumping them all in a big pile and expected everyone to go through the pile looking for letters addressed to their own name. It may sound inefficient, but it works well enough on small networks. Be clear, however, that Ethernet is concerned only with sending data on the local network. The Internet is a network of networks, so the data we send needs to hop from one network to the other. And so specifying MAC addresses is not sufficient. We need an additional layer of addressing, hence the Internet layer. So, when we're sending Internet traffic over Ethernet, the data in the Ethernet frame will consist of a chunk of Internet Protocol data, what's called an IP packet. Each IP packet consists of first a header and then the actual data being sent. The IP header, of course, contains information about that IP packet, most importantly, the destination IP address. But then we need to also specify which program on the computer is intended to receive the data. And so inside of IP, we use one of the two transport layers, either TCP or UDP. Here in this case, we're using TCP, and a chunk of TCP data is not called a packet, it's actually called a segment. Though, just like IP, it begins with a header, followed by the actual data being sent. And UDP looks very much the same. UDP begins with a UDP header, followed by the actual data. Every TCP header or UDP header specifies a port number. Actually, they specify two port numbers. One to specify the program on the destination machine, which is to actually receive the data, and one to specify the program on the machine which sent the data. Because when data is received, we need to know not just which computer it was sent from, but which program on that computer sent it. And again, as I mentioned, TCP differs from UDP in that TCP does more than just specify port numbers, it also provides reliability, as we'll describe in detail later. Finally, contained within the transportation layer, we have the application layer, the data which programs actually care about, what they're actually trying to send and receive in the first place. Now let's look closer at these protocols. First, to understand IP, we simply need to look at the header. First off, an IP header begins with 4 bits which specify the version number of the IP protocol. The current version of IP is version 4 and has been in use for over 20 years. Currently, the Internet is in the early stages of transitioning away from version 4 to the next version, version 6. What happened to version 5? Well, there were some proposals which were labeled as version 5, but they didn't go anywhere, and so the version that's coming is version 6. Version 6 was actually concocted over 10 years ago, but adoption has been very, very slow, but it's expected the full transition away from version 4 to version 6 will take at least another 10 years. As it is here in 2010, the vast majority of traffic is still using version 4, so that's the version we'll discuss here. In any case, the next field is another 4 bits, and these 4 bits specify the length of the header. At a minimum, an IP header is 20 bytes in size, but some headers have an additional 40 bytes, so at max, an IP header is 60 bytes in length. Now, of course, if we're using 4 bits to specify the length, well, that's only the values 0 to 15. So the way this works is that the length is specified in multiples of 4. So for example, if this field has the value 15, well, 15 times 4 is 60. 60 bytes, that's the maximum IP header length. The next field, the Differentiated Services Code Point, or DSCP, is made up of a few bits which effectively mark the priority of that packet. Now, of course, the problem is you can send as many packets marked as high priority as you want, but if that priority isn't respected by the networks along the way which are going to carry those packets, then it doesn't matter. So in fact, many networks will often just ignore these bits, or some networks will only observe these bits for packets originating within that network itself. The next field, the Explicit Congestion Notification, is also very often just ignored. The idea is that the sender can notify the receiver of the congestion conditions on the sender's end of the network. But of course, it's up to the receiver to respond to this notification intelligently. So for example, if the computer you're talking to tells you that it's currently experiencing congestion, that's a hint to you to back off and not send so many packets. The next field specifies the entire length of the packet, including the header, in bytes. And so because this field is 16 bits, well, the maximum value is 65,536, hence the largest possible IP packet is 65,535 bytes.